Picture this. You're in a Formula One pit stop. The clock is ticking down relentlessly, millions of dollars are on the line, and literally a single fraction of a second's mistake, it cost you the entire race. Well, that is exactly what sitting the IGCSE Computer Science Paper 1 feels like. You're racing against the exam clock, and your fundamental understanding of data representation, that's your engine. If there's even one loose bolt in your logic, the whole machine just breaks down. So in this explainer, we're making absolutely sure that your binary engine is perfectly tuned.
Okay, let's dive right into this. Take a seemingly simple calculation. 110 plus 222. I mean, any basic pocket calculator is going to tell you the answer is 332, right? So, why, on a computer science exam, could this exact calculation result in 76? No, it's not a typo. It is a fatal exam error just waiting to happen. See, if you don't understand the hidden 8-bit limits of the computer system you're actually analyzing, you're going to bleed marks on your paper without even realizing it.
To understand why that happens, we kind of need to rebuild this engine from the ground up. And what's truly fascinating here is just the sheer simplicity of the underlying system. A computer, no matter how incredibly complex the software is, completely relies on a base 2 number system. It's literally just ones and zeros. And these simply correspond to real, physical, on and off states right inside the hardware. So, when we lay out a standard 8-bit system, our heading values build from right to left, doubling every single time. We go 1, 2, 4, 8, 16, 32, 64, and finally 1 to 28. That represents 2 to the power of 0 all the way up to 2 to the power of 7. Seriously, burn these heading values into your memory. This is your mental dashboard.
And this setup brilliantly illustrates how we convert positive denary numbers, the everyday base 10 numbers you and I use, into this machine-readable binary format. Honestly, the most bulletproof way to do this in an exam is the successive division method. Step 1. You take a denary number, let's say 142, and you divide it by 2. That gives us 71, right? With a remainder of 0. Step 2. You just record that remainder on the side. Step 3. You repeat the whole process with 71. That gives you 35, remainder 1. You keep going all the way down until your division actually results in 0. Now, Step 4. This is where students always slip up. You absolutely must read those remainders from the bottom to the top to get your final answer. So, doing that, 142 successfully becomes 100001110. It's a simple, reliable algorithm, and it works every single time.
Now, let's see how this builds when we need to really scale up our engine. Binary is totally perfect for the machine, sure, but humans? We need something a bit more compact to read when we're dealing with massive amounts of data. Enter hexadecimal. It's a base 16 number system. It uses the digits 0 through 9, and then it switches to the letters A through F to represent the values 10 to 15. The headings here scale up drastically. We're talking 16 to the power of 0, 16 to the 1, 16 to the 2. We won't dwell too long on this right now, but just understand that this is exactly how your engine scales up for complex computing tasks without, filling screens with thousands of tiny ones and zeros.
So, okay, you know how to build the basic numbers, but in just a few minutes, I'm going to share an examiner clue that completely changes everything you know about shifting these numbers around. I mean, what actually happens when a logical operation literally drops vital data right off the edge of your allocated space? Sticking around to see this is absolutely going to be the difference between getting a top band mark and just an average one. But first, we need to set up the foundational framework that makes this clue so glaringly obvious. Let's get back to that impossible math from the beginning and really escalate the stakes. Let's walk through the step-by-step binary addition for 110 and 222. That is 01101110 plus 11011110. You line them up exactly like you would in traditional math, but you have to follow the absolute binary rule. 1 plus 1 equals 0, carry 1. And if you end up with 1 plus 1 plus 1, well, the result is 1, carry 1. Notice those carry values rippling down the addition toward the far left, because as we get to the end there, something catastrophic is about to happen to our final sum. Remember that mental dashboard we built earlier? 8 bits. That is the allocated word size we're dealing with in this specific scenario. If you add up all those column headings, 128 plus 64 plus 32, all the way down to 1, you hit a hard, unbreakable ceiling, 255. That is the absolute maximum possible value an 8-bit word can hold. Literally, there's no room for anything bigger.
And this brings us right to the fatal flaw, the 9th bit. When we added those two binary strings, that final carry calculation actually pushed a 1 into a 9th position. But our computer architecture in this example only has 8 physical slots, so that 9th bit, it literally falls off into the void. It's just gone, and the 8 bits that are left behind happen to form the binary number for 76. The machine genuinely thinks the answer is 76, which, of course, we know is completely incorrect. This generation of a 9th bit exceeding that 255 maximum is called an overflow error. It completely, utterly ruins the integrity of the data.
Now that we deeply understand the absolute danger of those physical boundaries, let's look at how we manipulate numbers inside them. Let's take an original 8-bit number, which has a denaré value of 54. We're going to perform a logical shift. If we shift every single bit 2 places to the left and just fill the newly empty rightmost slots with zeros, our new value suddenly becomes 216. Think of it this way. Shifting left is literally the exact same thing as multiplying by factors of 2. So, 2 shifts to the left equals multiplying by 2 to the power of 2, which is 4. And 54 times 4 equals exactly 216.
And this brilliantly illustrates the payoff to that big question I asked you a few minutes ago. What happens when we shift too far? Well, if we take that exact same 54 and logically shift it 4 places to the left, mathematically we should get 864. But check out what happens to that 8-bit boundary. Those 2 leftmost 1 bits drop entirely off the edge of the register. The new binary left behind reads as 96. We have permanently lost data. An error is instantly generated because our logical shift just forced critical bits right out of the allocated word size.
All right, I want you to pause this explainer right now and predict the outcome of this challenge. We have the binary number 00110110, which again is our trusty 54. I want you to logically shift it right by 1 single place. Remember the rule we just talked about. If shifting left is multiplication, while shifting right is division. So grab a piece of paper if you need to. What is the new binary value and what is its denary equivalent?
Okay, let's see if we cracked it together. When you shift the bits 1 position to the right, that rightmost 0 drops off. Then, you absolutely must pad the newly empty leftmost position with a 0. So you end up with 0001111. And since shifting right divides by factors of 2, 54 divided by 2 to the power of 1 is 27. If you got this exact result, congratulations, you just perfectly secured those marks. But here's the thing. Knowing the math is really only half the battle on a Cambridge paper. You need the explicit upgrade framework. That is concept, evidence, reasoning, and examiner wording. See, it's not just about what you know in your head. It's exactly how you phrase it on the actual exam page to unlock those top band marks, especially when you're dealing with tricky scenario questions.
Let's compare 2 different answers to see this framework in action. First, think about a flawed, highly typical student answer explaining why our addition failed. They might write, "The number got too big." 0 marks. It's vague, it's completely non-technical. Now, let's apply the framework. The sum generated a 9th bit exceeding the maximum 8-bit value of 255, causing an overflow error. Boom. Concept, evidence, reasoning, examiner wording. That exact phrasing is exactly what the examiner is hunting for.
Okay, rapid-fire revision checklist before we finish up this pit stop. Number 1, apply scenario nouns. If the exam question talks about a factory temperature sensor, your written answer must specifically mention the temperature sensor, not just generic data. Number 2, remember that 1 mark generally equals 1 distinct technical point. Don't waste time repeating the same idea twice. Number 3, watch your command words closely. The word explain requires a totally different depth of writing than just state. And number 4, always verify your boundary data to ensure your calculations haven't secretly triggered an overflow error.
Really quickly before we move to the final, crucial piece of the puzzle, please take a quick second to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've got so much more coming your way.
All right, so we have successfully locked down the technical mechanics of binary, overflow, and logical shifts. You have the knowledge, but what actually happens when the examiner sets a trap in the command word itself? Think about it. You could have absolutely perfect technical knowledge, but if the question format tricks you into describing when you were actually supposed to evaluate, you're going to leave that exam hall feeling super confident, only to receive 0 marks.
See, understanding the math clearly isn't enough if you fall for the structural traps. The next explainer in this series covers common traps by question type. And honestly, it is the mandatory next lap you absolutely must take to pass paper 1.
It's going to unpack exactly how to navigate those command word tricks so your perfect knowledge actually translates into perfect marks. So ask yourself, are you truly commanding your binary knowledge, or are the exam commands secretly trapping you? Jump over to that explainer right now, and let's keep this engine running.